Yeah, so let's start. So welcome everyone. So pleasure to have Debraj Chakraborty among us today. So Debraj finished his PhD from Belgium, Université Libre in Bruxelles in Belgium, and then he is joining at the postdoc in Czech Republic in a month or so. And in between, he is visiting India as well as he's here in India for a few weeks. So he's going to talk about Monte Carlo research with advice, and he primarily works in formal method with some focus on using learning techniques in formal methods as well. So yeah.
Thank you, Shivasis, for inviting me. And today I will talk about Monte Carlo research with advice, which is the results I had during my PhD with Professor Rasta at ULB, and this is a joint work with Damia, Shivasis, and Guillermo. So we are interested in systems where we have a controller that takes some decisions, and there is also some uncontrollable behavior that is modeled by the environment, and based on what the decisions the controller takes, we get some kind of a reward. So the objective is to find the optimal strategy for the controller in the system. And there are two different ways to do this. One is with formal methods, where in model checking, where we systematically construct the whole model and then check all the properties in all states. And this we have the exact algorithms, but the problem is that it has the state explosion, where the number of systems increases when we have a larger system, and that may exceed the available memory. So while it has strong guarantees, it doesn't scale to larger systems. Whereas we also have learning-based methods like heuristic searches or machine learning. And these are not a complete method, but it doesn't have the problem of state explosion. So while this gives weaker guarantees, it scales to much larger systems. So the objective here is to talk about some hybrid algorithms that scales for larger systems, but also provides guarantees. And in this presentation, I will talk about Markov process, which is a model to represent such systems. Then I will talk about Monte Carlo research or MCTS, which is a simulation-based heuristic search algorithm. And then I will talk about how to augment this MCTS with techniques from formal method using something called symbolic advice. And then at last I will talk about how to use a neural network to imitate and replace this symbolic advice in MCTS. So first to talk about Markov process, which is used to define a system with discrete state space where the environment works with a stochastic distribution. So Markov process is generally denoted as a directed graph where we have multiple states, and from these states we have different actions which are controlled by the controller, and then whenever some action is taken, with some probability the state changes. For example, suppose we are at this state, and also whenever the actions are taken, there is some reward associated to it. So currently the reward is 0, and then suppose the robot here takes this action, then with some probability it would go to it would go to the next other state, and then we have a reward of 2. Then from here it has the option to take this action, then with a probability it can go back to the previous state, and then the rewards are augmented along the way, and so on. So this is how we can describe a path in the Markov-Richan process.
So what is the reward 1?
So it's the total reward thing now. So initially it was 2, then we get -1, so it becomes 1. And a strategy is a function from finite paths in the Markov in the MDP to set of actions that the controller can take. For example, here from this state, the action run, and from this state the action stand is a. This could be an example of a strategy. Now, when we fix a strategy, this creates a Markov chain. For example, when we fix a strategy, we get a Markov chain like this, and there the finite horizon reward for a length h is the expected reward we get for pass of that length h, and the infinite horizon reward is the expected is the expected average reward when the h tends to infinity. So the optimal strategy that we are looking for is the strategy that maximizes this infinite horizon expected average reward.
So you're not looking at discounted rewards.
No, we are looking at.
So I thought in Monte Carlo that would make sense. Then you can truncate after a while.
Yes, but we
Do something else.
And when you were talking about the strategies, it can be any arbitrary ones, or you were talking about some finite memory, or so when you say this arg max over sigma, so the sigma can be arbitrary.
In general, it's arbitrary, but I mean, for the example that I showed, it was a memory. But in general, we can have arbitrary strategies.
So your Markov chain can be infinite.
Yes.
Usually both will know about the deal.
No, so I don't know why my name appears there.
So let's give an example of a Markov chain. So we can model the game of Pac-Man as a MDP, where the Pac-Man objective of the Pac-Man is to eat all the foods while avoiding the ghost. So in this case, the controller controls the action of the Pac-Man, and we can assume that the ghost follows a probabilistic model. So in the MDP, the stochastic transitions are the moves of the ghosts, and the states in the MDP, they have the knowledge of the position of every agents and what the foods are left.
So the ghosts are stochastic or adversarial?
In this case, we assume that the ghosts are stochastic.
Okay, so it doesn't depend on. So their actions doesn't depend on what the actions you have been taking.
Yes.
So okay.
So whenever Pac-Man eats the food, it gets a reward, and whenever it loses, I mean, gets eaten by the ghost, it gets a large penalty. So even with such a small grid, the MDP that we can construct is really big. So for example, in this case, we get an MDP of 10^16 states. So for this, we cannot really do the exact algorithm from formal methods to get the optimal strategy.
Has anybody applied these techniques to Pac-Man? Has anyone actually applied this machine, this Markov decision process kind of technology to?
Yes, I think.
Yeah.
Yes. So for this, we took an online approach like receding horizon control, where suppose we are in the MDP, suppose we are at this state S0, then we look at the unfolding, and starting from this state S0, and then we fix the horizon H, and then we try to, instead of optimizing for infinite horizon, we try to optimize for the total reward in this window H. And then when suppose we get a strategy, and then according to the strategy, this action A1 is the best action from this state S node. Then we play the action A1, and then we go to the next state. For example, we go to the state S2. From there, we again calculate a strategy that optimizes the total reward in horizon edge. So theoretically, if the horizon is large enough, then it will be close to the optimal strategy. And but even if when the edge is not large enough, what we do is we define some kind of heuristic terminal rewards to the leaves of the unfolding tree that kind of estimates the long-term behavior, saying how good the leaf state is. So this way, instead of doing for infinite horizon, we are doing we are doing in an unfolding of depth edge. So there we can use the MCTS.
And how do you get this terminal reward? It's like you.
It's kind of heuristic, and it depends on the problem we have. So we can kind of trial and error way to define it.
I mean, you can always construct a problem where any edge is not enough, right?
Yes, because we can
Everything
always
happens
have
after that.
the bad thing at the end of the.
That's why discounted may have been a good way to discounted rewards.
Yes, also.
You can think about that because there's not literature on that. You can use that.
Yes. So even with the fixing the horizon, we get a very large unfolding. So what we do is do some kind of heuristic. So a naive heuristic would be to judge for each action, we simulate some paths to approximate how good the action is, and then we select the best action at the root. But this is kind of a naive way, and more a better, more clever, and more popular ways to do Monte Carlo research, where we kind of iteratively construct a search tree with the estimates how good an action from a state is. So suppose at some iteration we have this part of the search tree built, then what we do is starting from the root node, we using some strategy, we traverse the tree till we found a new tree that is not new node that is not already added to the tree. And then we add this node to the tree, and to get an estimation how good this node is, we use simulation to get a value, and then we backpropagate this value to update the estimates in the tree. And thus in the iteration we add more nodes to the search tree to create this tree, and at some point when our budget of time or the number of iterations that we have ends, we output the action that has the best value at the root.
So is this all policy simulation or all policy simulation?
So this we are doing online. So I mean, so from each state we are doing MCTS to find the best action.
So you are simultaneously playing the game as well.
Yes. So it's on the play. And now, and the formal guarantees that we get is that when we use the UCT or upper confidence bound strategy during selection, then after some given number of iterations, MCTS outputs the best action. The results that we have, there is for the MCTS is that the probability of getting a suboptimal action converges to 0 with an increasing number of iterations, and these value estimates converges to the real value estimates at a speed of order of log n by n. N is the number of iterations.
And yes, there is no difference on number of states.
So actually it depends. So this order of thing is hidden there.
So like, I mean, so for example, this kind of thing is called like this chess programs use exactly this, right? So there that constant.
Yes.
So few things. So you're just finding for a particular state, you're finding a value function. You fix the state, you're doing all of this in your
Yes, so from the current state.
in the given state.
Yes.
So the fact that from that state, you visit a lot of other states, you learn about them, you're ignoring all that.
Yes.
I see. And then typically central limit theorem gives you convergence rate of 1/10. So how are you getting better than that for estimating value? Or you're saying value within some epsilon or something? Is that what you mean? Or?
Actually, which one?
When you say BI converges to real value of AI, typically, BI is some kind of expectation, right?
Yes.
So it has a central limit rate of convergence of 1 square root of n. So you're showing a faster rate of convergence. But presumably for you, convergence means that you get within epsilon of the true value. Is that what you mean?
But the number of states he's seeing is significantly more than n, right? It's the number, n is it?
N is the number of iterations.
Why? Yes, that way. N is the number of,
And it's not a mean of just one.
but somehow still they should be related to central limit theorem.
Yeah, because there's no mean happening.
BI, I mean, it's going to be once you kind of fix the policies that you go down, then it's just evaluating the policy. It can't be better than,
Yeah, but it's much worse than.
yes, that's what I'm saying. Okay.
The depth. N is a depth. And so the number of nodes.
No, N is the number of iterations. So number of nodes currently added.
Oh, number of nodes added to it. Yeah, then.
Sorry, number of nodes for?
Added to the.
In each iteration, we are adding one node. It's the number of iterations.
So then it's much faster.
No, so it's probably that he's saying within epsilon. Then you're kind of sitting at,
See, so what does speed?
Yes. So it has the epsilon thing.
So as in, so what is, so like, to get to epsilon, you need how many steps? Like central limit theorem would say that to get epsilon, you need 1/epsilon squared steps. Or 1/epsilon squared samples. So what is that quantity?
So I mean that this is the epsilon thing.
Well, this should be it.
But N is the number of iterations.
So we will additive. You mean additive constant or multiplicative constant?
Additive.
This is additive constant.
So what I mean is that this value, this value that MCTS gives and the real value, the difference is order of log n by n.
But you are actually using some heuristic policy to evaluate the leads, right?
Yes.
So you're assuming that those heuristic is like in expectation.
Yes, I am assuming in that these heuristic values, the way I have it, they are very small. So they only matters when two paths have almost similar values, then only they matters.
So you mean it's unbiased estimate. The heuristic for the leads. So you're running a heuristic policy to assess the lead, right? So the value that is returned by the heuristic is an unbiased estimate of the actual value. So this is what you are assuming.
No, so it's I did that as
Okay. So there is some very simple thing where there's only one state and I keep returning back to it. Then when do I get any information? So if suppose there's only one state S0, it has some value which I don't know right now. And then I start expanding this tree, I just keep seeing S0 again and again. So there at some point some information has to be fed into this data about the value.
So the function that we define some, for example, in case of Pacman, we define when we give a value, we say a state is good if the hosts are far away and the foods are close. So we give a function based on the relative distance to the food and relative distance.
So there is some heuristic thing at the bottom that is, and that is this there's some expectation that is also decent or good or something.
Yes.
Right. Okay.
And this basic action is over this horizon edge that is starting.
Yes.
I would only from the top.
We're also simulating the horizon edge.
So in the case of the games, you only get to see the value only at the end of the game. So there is no reward or associated as such per action, right?
But in case of Pac-Man, there is the reward. So if you eat food, you get a reward.
Okay, so it's not like chess. Okay.
Oh, that's it. The reward is also the information.
So, yeah. So we talk about something called advice, which is a way to inject the domain-specific knowledge using formal methods in the MCTS. So we can think advice as a set of finite paths which can be defined symbolically as a logical formula like LTL or SAT or any other logic. So in some way it says that some paths guides the MCTS saying that which are the good paths in the tree and which are what the good strategy lies. So when we say that some paths are good, some paths are bad, this kind of gives a leaf leveling of the tree, and when we go bottom up, this will tune the unfolding. In such a some way, the advice defines the pruning of the unfolded MDP. So what it basically saying is that when we search for a good strategy, this grayed out part, this can be ignored.
But so it could be that my advice is also adversarial in the sense you don't have any control over the quality of the advice, right? So are you assuming that advice is always good? Like
No, so advice is I am giving it, so I try to give a good advice.
but how do you get this advice?
So it would depend on the system. So I am.
So in case of Pac-Man, you already have, let's say, advice for each configuration, something like that.
So I'll give the example what advice for Pac-Man is.
And you say like you can have these LTL formulas, but LTL formulas can be over infinite paths, right? I mean, in general, you can.
Yes, but
The semantic can be, but here you are talking about.
okay, so maybe PCTL path formula kind of thing, right? I mean, G of less or equals H.
For that length.
So there's a state S0. Suppose I have a very simple tree, there's only one state S,
Yes.
which gives a reward with probability P, a reward of 1. And in my heuristic just says the reward is 1 or some number, it says the reward is 1. So then if I do H levels, I get like sum of H Bernoullis with P plus that 1. So if I take the mean, so there is a 1 over n error that is coming just from the heuristic being bad, and plus there is a 1 over square root n error that is coming from the central limit theorem. And so how do you get log n over n? That's very. So my point is, so suppose you have just one state, your tree has a function, it's a very simple system.
Yes.
And so whenever you run, you just get back the same state, and that state has a probabilistic reward, which is 1 with probability p, 0 with probability 1 minus p. So now if I run it for H, go to H levels, then my estimate of the reward will be like H over n, whatever, P over so whatever, it will be sum of H Bernoullis, Bernoulli P's divided by H, plus the heuristic value divided by H. The heuristic value divided by H is going to 0 at the rate of 1 by H. But this one, the sum of this H Bernoulli, so that has expectation correct, it is P. But its variance is of the order of 1 over root H.
H is the horizon.
Yeah, H is the.
Yes, but
So and H also
the H is also the constant. So it's also in the.
No, so n, the number of states expanded is n also in this. So
My understanding is that suppose you want to estimate the Bernoulli's mean to epsilon accuracy, you need log n sample or log n number of sample. And now he's averaging it by n or something, he's normalizing by n, so that's why he's log n upon n. I'm guessing that's how it works.
So you can look at the original paper. So what they do is they assume that this is a bandit problem where you have two actions where you need to find which action is better.
So that's a different problem. Finding which action is better, you can do log n.
the number of samples you need is 1 over epsilon square log 1 over delta.
Yeah.
So delta, so then,
So what about talking about it?
oh, that is, so the only the error probability. Epsilon is some fixed.
Epsilon is fixed, yes.
The accuracy is fixed, the accuracy parameter is fixed, only the error probability.
And when you're comparing two arms, then epsilon doesn't come in, right? Then it's just you need login, order login number of samples to. The one arm is better than the other.
Yes.
There is.
So I thought that epsilon is the log over n, right? And when you say the convergence, it's like the value is away from the original one, that is log over n, and that's the convergence, like with a where n is the number of iterations. So isn't that the epsilon? Or, and that's what
That scale like one of them.
Mhm.
Yeah, we will be after.
Okay.
So, for example, in case of Pac-Man, we can, when Pac-Man gets eaten by a ghost, we want to avoid these steps in these states. And so these unsafe states, we can say it as for all ghosts, the position of the Pac-Man should not be same as the position of the ghost. And this can be modeled as a formula which says that always this unsafe state should be avoided. So this way we have an advice that is set up the safe paths. But the problem is that Pac-Man cannot really enforce this, because in this case, suppose Pac-Man goes towards the red ghost and the red ghost goes upwards, then it's a safe path. But it is not advisable to take this path, because when Pac-Man goes towards the red ghost, the red ghost path can also comes towards Pac-Man, and then it will be an unsafe path. So the more stronger advice would be that take all the paths where safety is ensured, no matter what stochastic transitions are taken. So we talk about something called enforceable advice, that is the set of paths where every action is compatible with a strategy enforcing safety.
So safety for only the last iteration. So only for the last step, immediate step.
One step.
One step.
No, so no, it's age.
But let's say, I mean, if you are only ensuring safety, so for example, let's say at a given time, it might happen that it might look that this state that they have been taking a state, say for let's say for 1 or 2 iterations. But this might eventually lead up to some kind of bottleneck where you can't escape.
Yeah, so
Yes.
this one protector is.
Yes, this will be make you safe for each step, but not much.
Okay, so it's each step.
Yes.
But this is the formal methods kind of point. You can kind of at some stage basically give guidance.
Yes.
That's what you.
But anyway, in case of Pac-Man, we can always have, when Pac-Man is not safe, right? It's because you can always have cases where the ghost attacks you from multiple directions. So it's better to have.
So is it like this for edge steps, you assume the ghosts are adversarial and then you check this? So is this enforceable advice similar to saying for the edge horizon, you assume that the ghosts are going to be adversarial? Even then, you will be safe.
Yes.
I guess.
Yes. Yes. So
Yes, there is no probability, right?
I will come to the probability later.
Okay.
So to compute enforceable advice from the original advice, we can say that the action A0 is compatible with the enforceable advice is if for all next state there is an action such that for all next state this whole path is a safe path. And this can be formulated as a 2-player game, and we can get strategy. And also,
So what is your psi here? So phi is the advice, right?
so psi is the safe advice that says that path which is safe for next 8 steps. And phi is the enforceable advice that is saying that whatever the host do, you will be step for next stage steps. So this enforceable advice is enforced by some strategy. And also we can have this site encoded as some Boolean formula and use UBF solver to iteratively construct this enforceable advice. But the thing is that this is too restrictive because sometimes there may not be a strategy. For example, if the pacman gets attacked by ghost from all directions, we will have an empty advice. So for this, we also try take the qualitative approach where we talk about the probabilities. So we enforce safety as much as possible. So from state X, S0, we take the action that maximizes the probability to stay safe. And this gives us a advice enforced by a less restrictive strategy. And this can be computed using some model checking tools like Storm. And another thing is that when we calculate this strategy, we can look it in a smaller MDP where we do not need to consider about foods or the course that are very far away because we are checking for the safety in a finite horizon.
So here you are restricting your strategy to be like a memory-based strategy, right? Like you say, sigma is 0 equal to A. So when you say
not memory-based, but S0 is the initial state. So
okay. Oh, I see. Okay. I see.
Sigma is random.
and S for also.
And can you just go back to that slide where you had this the alternation of the quantifiers, like you had some for all exists for all. So this is so this will be like age alternations or something like that for age. Okay.
It must be quite difficult to compute these things, right? Although you're saying you can use problems with it.
Sorry?
Must be quite expensive computation need to compute these things.
Yes.
Back then would have billions of states.
But still, we are looking at fixed storage and not the whole billion of states. So for the Monte Carlo research, that is for pacman. What we can do is during selection, we at the root we can select among the actions, and that maximizes the probability to stay. We maximizes the probability to stay safe, and during the and now since we in the selection we are ensuring the safety as much as possible. During when we are simulating, it is enough to simulate among only the safe paths.
So for this, we need to know the probability distribution, the probability that the hosts are using.
Yes, in the model checker when
But
we use
is it like no, is it not like a very strong assumption that you know the probabilities?
Yes, I think so. So we maybe in future we can think about learning the probabilities, but right now what we implemented was that we know the distribution. So for simulation advice, we simulate only among the safe paths, and using this kind of selection and simulation advice, we ran our experiments, and for horizon 10 and in MCTS we have 40 iterations, and in each iteration we have 20 simulations, and there we have this kind of results, and we say that the game is drawn if even after 300 steps pacman doesn't eat all the food or doesn't get eaten by the ghosts. So there with MCTS
Who is the lead?
You are you share.
So In MCTS we advice, we get like 8% of the win. If we add the selection advice, we get 36% win, but we get very big number of draws where Techman is good at avoiding the force, but not really good at getting all the force. The best result that we have is when we use both advice, and there in the grid that we had before, we get 90% win rate.
So what is the grid size? Like, what is the game?
The grid that was it was 21 times 9. But with 4 cores, that's what moving uniformly at random. So, in conclusion, for Monte Carlo research, what we do is we select actions in the unfolding pruned by a selection advice, and we simulate according to another advice that is called simulation advice. So we use 2 different advice.
So it's, your Pac-Man going around, every time you reach a state, you construct this massive tree where every state has further many states, many states and all that. And after solving a massive tree, the tree decide what they actually take at that particular state.
Yes.
And then the game moves on, and then you keep on doing this again. That's how long did the simulations actually take when you actually ran them? Days, months?
I mean, yes, it does.
Yeah.
So we
But
showed that
then, like, I think we have this question about this online thing, so maybe like it's an online policy, so
yes, so we will come to that later. So we talk about replacing the model system. So we show that the convergence properties are maintained when the selection advice is enforceable and it is not pruning the optimal actions and for any simulation advice. So there is also, and we also use this in for another example where we schedule hard and soft tasks, and this was our work with Shivasis. And there we talk about task system. So hard tasks are tasks where we should never miss the deadline, and soft tasks we can miss the deadlines, but this will have some positive cost. And formally, the tasks are taskers where we have a relative deadline of the. So the task where it is having many instances called jobs, and D is the relative deadline when the job should end, and we have a fixed and a C, which is a distribution over how much time the job should take, and another distribution on in what arrival the job instances of the tasks are coming. And this is measured, we assume that the time is kind of discrete, so measured by CPU ticks, and we want a scheduler that decides which active task it should give the CPU access. And this can also be modeled as an MDP where each state would have following informations that for each task, what is the remaining time to the deadline, the distributions over possible remaining computation time, distribution over possible time till when the task arrives, and the action is the action for the scheduler where it either schedules task or stays idle. And the stochastic conditions are either finishing or killing an active task or submit a new task according to when the tasks are coming. And we have the costs where the soft tasks are missing their deadlines, and this can be thought as a negative reward. So the objective is to find a strategy for the scheduler which avoids the states where some hard task misses their deadlines and also minimize the expected mean cost rate, which are results from the soft tasks missing their deadlines. But there also we have the similar problem where model checkers can only handle tasks which are relatively small. Like even with like 5 tasks, we have an MDP with 10 power 6 states. So there also we use learning-based methods like MCTS or deep Q learning, and So previously in Catchment, there was no safe strategies to always avoid the ghost, but at least in this case, there are actually some safe strategies that we can, if we follow them, we can avoid the hard task missing their deadlines. So we use some kind these safe strategies, advice enforceable by these safe strategies when we do the MCTS, and also when we do deep learning. During simulations, we use the strategies to seal the simulations so that no hard task misses their deadlines. Now let's talk about what kind of safe strategies that we can have. One is the earliest deadline first strategy, where we schedule the hard task, we set the earliest deadline, and if no hard tasks are active, then we only schedule soft tasks. And this is a strategy that make sure that hard task doesn't miss the deadline, which is easy to calculate but too restrictive in comparison to the most general scheduler, where we allow all actions that are compatible to some safe strategy such that no hard task misses their deadlines. Now this allows maximum exploration, but it needs to be pre-computed to use as a shielding or the advice. And so we show some results where we have different task systems, where, for example, here we have 2 hard tasks and 10 soft tasks, and we see that using as model checker like storm, if the tasks MDPs generators are really big, then we get timeouts, and we also compare the results we get from MCTS and results we get from deep learning. We see that when we do not use any kind of shielding, what we get is that the strategies that we get, the hard task misses their deadlines. So this is denoted by these infinities. And if we use as a advice something more restrictive, then we get strategies that has higher cost than if we get advice which is less restrictive, like the most general strategy. And similar for deep learning, during shielding, if we use EDF, which is more restrictive, we get things which has cost higher. And to compare the MCTS and the deep learning, what we have is that deep learning MCTS was good at finding better cost optimization strategies in comparison to deep learning.
So now I presume in deep learning, this Q learning means you have this for every state and every action, you find the optimal reward.
Yes.
So somehow you're learning that using this deep learning. So
yes, so that Q values, instead of saving in the table, you use a neural network.
So what's the input to the neural network and what's your, how do you train the network?
So
Yeah.
I think so do you know what we had in the,
So we had
Yeah. But this is not quite it's not supervised learning, right?
no,
Yeah.
it's not supervised.
I think you run at least the chess programs that use it, they just run, where you play against yourself.
So we were similar to functional approximation where you just use this deep network as a functional approximator. What is that?
yes.
Yeah, no, but I just thought maybe PBS can be spelled out. So I mean every time there's a transition, you get information about.
So they were using more like this reinforcement learning kind of thing. And so finally it will, like, you learn for long enough time, but some of them even still do not converge well.
Okay, so you kind of run this Markov decision process, you do a transition, and that feeds into what you're
Yeah, so you kind of observe at every time, like how much is the cost that is happening, and that feeds, goes back, and then it's like the early kind of.
Good, if you have a slide which kind of explains exactly what you think that maybe the next slide will be better.
No, I'm just showing the results. Okay. Yes.
What is NA in some of those?
Oh, so this is, I'm saying not applicable because in this task system there is no hard task, so we do not have the strategies where a hard test doesn't miss in their deadlines. So coming back to the previous results about Pacman with MCTS and the simulation advice, we to compute the MCTS and the simulation advice we took like 9 seconds, and to compute the selection advice we took and when we are using MCTS in both advice, the computer selection advice takes 8.4 seconds. So these parts are done in Python by us, so there is still chance to decrease this time to something very small. Even we can do some kind of parallelization, but this part uses some model checker that is already optimized, so we cannot really decrease the high latency that we get from this model checking tools. So using model checker as an advice is costly in terms of time, and it is not really practical. So what we do is we replace the symbolic advice with something called neural advice, where we use a neural network to imitate the advice that the model checker gives. So we use the neural imitation learning framework where we try to mimic the strategy that we get from the model checker. So to give an example, let's talk about another MDP, where this is called frozen lake, which is also a grid-like structure like Pacman, but it's smaller. It gives a smaller MDP where we have walls, and this is a frozen lake where is some holes, and there is a target where the robot needs to go. But since the lake is very much slippery, so whenever robots like to go to a direction, with some probability it ends up going to different directions. So the objective of the robot is to go to the target while avoiding these holes. And when it reaches the target, it gets a reward. And these holes are the sink state, so when it goes to the hole, it cannot reach the target anymore. So this is also modeled by an MDP, and the strategy where we are interested in is not only should optimize the probability to reach the target, but it's also we want a strategy that helps us to reach the target quickly. So we need to optimize from a state. Yes, we need to take the action which optimizes this value of sigma, which is optimal in terms of reaching the target, in terms of optimizing the probability to reach the target, and also minimizes the expected distance towards the target. So we calculate the model checker with exact algorithm will calculate this function, and then it will take the strategy will be from S, take the action that minimizes this function. Or we can use some kind of heuristic Monte Carlo research where we will have some where we will have from state S, we will take the action that optimize the method maximizes the values given by the MCTS. So in imitation learning, what we do is we train a neural network that would learn this function f sigma or this value given by the MCTS. So, and when we learn this, when we train a neural network, the learn strategy would be to from state S take the action that optimizes the value given by the neural network. So but the problem is that how we can evaluate the strategy we learn, because the traditional approaches in learning in evaluating a neural network like calculating the loss function or the accuracy would not work, because we can have the cases that error in one critical state can be enough such that the strategies would perform bad. For example, look at this process where suppose in all state the neural network gives the exact values, and then the strategy we get from neural network matches with the original strategy given from the model checker. But in one state like this, instead of going to the target, it says go to the goal. But then even when the strategy has a nice accuracy, it would be a bad strategy, because using this strategy you will never win. So we use statistical model checking to compare how good our learned strategy is instead of checking for loss function or accuracy. And by statistical model checking, I mean we have the strategy, and using the strategy we simulate a set of paths and then compare the statistics. For example, in this case, we can compare how many times it wins or how many times it loses. So with frozen lake, what we have is we tried using storm and MCTS, and in both cases we get a strategy, and then using imitation learning we learn the strategy, and then we see that the strategy we learned from storm gives 81% win rate. That means that in 81% time of the time in frozen lake it reaches the target, and in case of strategy learned from MCTS it gives 69% win rate. So we can from this we can say that the data extracted from an exact method like model checking would give a more noise-free data than compared to data extracted from MCTS. So we will learn a strategy from, and we will learn a better strategy from the model checker.
How will your loss percent go down? So you're losing less after learning the strategy.
No. So this is the original strategy, and this is the strategy that I learned from.
After all, you lose less. You lose less. You're winning less, but you're also
Yes, but this is a really bad one. So it doesn't go straight to the target. It just keeps on looping around at the start position. So in Pacman, the advice we had was that we had the symbolic advice enforced by the strategy, which takes the action that maximizes the probability to stay safe. So what we do is, and this was too costly to compute in terms of time. So what we do is we train a neural network offline to learn this value that we are optimizing, and then the neural network would, so instead of using model checker during MCTS, we use this neural network and take the action that maximizes the value given from the neural network. But another problem is how we should generate data for the neural network. We can randomly generate states and actions in the MDP and to check if, and to get a data set and train the neural network. But this will give poor performance because it doesn't really find the interesting states or doesn't really represent the paths that we would see when we originally simulate the MDP. So there is the algorithm called dataset aggregation or DAGR, where we iteratively add more data to the training data set. So what we do is we start from an initial strategy and we generate states running simulation using the strategy, and the strategy, and in the states in these new simulations we add it to the data set, and then we from the bigger data set we run the strategy again. And this gives kind of realistic view of the states that can be frequently encountered. But still, this doesn't give really interesting data points where the neural network is not correctly learning. So what we propose is something called shard gather or shard dataset aggregation algorithm, where we add only the states where the neural network that we have is performing poorly in the dataset. And this kind of focuses on finding the states where the decision is crucial. And this way, this way of generating dataset gives us the better performance. So to show the results we try to find a strategy using the model checker storm which can make Pacman avoid ghost for 300 steps. So this is kind of more difficult than the original Pacman game, because where their Pacman needs to stay safe for till it eats all the foods. Here I am saying that Pacman needs to stay safe for 300 steps. And the optimal strategy that model checker gives, it has 70% mean rate. Now we use this counter example guided loop that we talked about, where we iteratively get more and more data, and using this we get some kind of 58 or 57% win rate. In comparison, if we have strategy learned for same data set of same size but randomly generated, we get a really poor strategy. Now, what we do is, once we learn this neural network, we do not need to use the model checker, and we can use this as the advice. So all these cases where we are using MCTS with a simulation advice, and when we are using simulation symbolic advice at the root, we are getting 90% win rate, but it was taking 8.4 seconds per step. Now, instead, if we replace this model check advice getting from model checker with the advice we get from neural network, we get 71% win rate, but we do not need this 8.4 seconds. So since we already have the neural network, we, instead of just using at the root of the MCTS, we can actually use it at each iteration for all the nodes, and this would not add much more time, because the neural network would, because asking the neural network for value would take time in maybe in microsecond. So this way, if we use the neural network, the advice given from neural network in all the nodes, instead of just at the root of the MCTS tree, we get win rate almost similar to the win rate that we are getting from symbolic advice, but with less time. And so in conclusion, what we have is, we showed a way to inject domain knowledge using model checker by something called symbolic advice, which is used in both selection and simulation phase of the MCTS. And we can preserve the convergence guarantees of the MCTS with the assumption that the advice we use in selection are enforceable, and it doesn't prune the optimal actions. And we can implement them using model checking tools. And to decrease the computation time for implementing this, we can imitate this advice by neural network. And we can generate the neural network by some kind of counter example guided dataset aggregation loop. And we say that we have multiple examples where this is working, this is giving good results. And this ends the talk.
So how does this compare with, for example, something like Cockpit? So there's a check engine called Cockpit, which does this Monte Carlo research, and at least the current implementation, I think does exactly this at the lowest level of the search. It has this neural network model, which is trained using the engine playing against itself. And it uses that to compute the value, like approximate the value at the lowest level. And otherwise, on top of that, it is doing a Monte Carlo. So is it similar or so it's the model checker thing is completely different. But this one,
I think it's similar, but it's a two-player game and they are.
I would see it. Yeah, there's no problem with it.
Yes, and also they have the chance to do the same play thing where it can play against itself.
Oh, so here there is, but this training thing here is, it's not playing against itself. It's playing still against place to traffic.
So your selection advice doesn't have the quantifier alternation, like if you write this symbolically in the formula, or will it also look like a
No, so we can
quantified QBL?
So we can write the selection advice as just the formula, and then we can say that we can get a strategy that gives that all the paths satisfy this formula. Like for safety, we can just the advice will set the safe path, and then when we get the action, then we can use the quantifier alternation to get a QBM formula and then solve it to get the action from the root.
No, so for the selection, you were saying that the safe paths, like the safe paths, they don't capture kind of all the roots of the.
Yes, so here I talked about two kinds of advice. First one was just the safe paths, but I then said that this cannot be enforced. So we use the defined advice. That is a strategy that enforces the safety, but that is also we can write it as a set of paths.
Yeah, so one was the selection one, which you had the QBL kind of a thing, but for the simulation also.
Yes, for the simulation we do not use the alternation because simulation we need to simulate a lot of paths, and there we cannot really afford the selection. Using the model check.
Okay, so yeah, let's end. So yeah, we can stop the Euclid. It's giving me can stop.